Dear colleagues, now we are moving to session 2 of this day, which will be devoted to sulfur management. Our speakers will present international experience of managing with sulfur and improving performance of refineries and petrochemical plants. And the first speaker of this session will be Stefano Mella, Global Product Manager, Temperature Engineered Solutions from Anderson Hauser. He will speak about accurate and reliable temperature profiling in hydroprocessing applications. Stefano's passion for mechanics led him to pursue a higher education in mechanical engineering, which allowed him to build a career in product management with Anderson Hauser, a global leader in measurement instrumentation, services and solutions for industrial process engineering. He complements his technical background with a deep understanding of oil and gas applications and an acute sense for business economics to drive innovation and customer-oriented solutions. Based in Germany, Stefano has an extensive track record in the customized temperature solutions business. His ingenuity has led him to develop innovative products such as the new iTherm Profile Sense, the sensor technology subject of his speaker contribution at this year's event. Our next speaker is our long-term partner, Wood, Scott Kafesian, Director Sulfur Technologies, will present on improvements in reliability, operability, and performance revitalize a vintage CRU. Scott is currently the Director of Sulfur Technologies for the Wood, formerly AMEC Foster Wheeler. Scott has over 30 years of experience in the technology, design, commissioning, startup, troubleshooting, and revamp of sulfur recovery projects worldwide. He has been with Wood since 2010. Along with his sulfur experience, he has a diverse background encompassing crude oil distillation, hydrotreating, gas plant revamps, gas compressor stations, and other industrial processes. He is also the manager of process engineering for the Salt Lake City office of Wood. Scott has a bachelor degree from University of California, Los Angeles, with ME and PhD degrees, all in chemical engineering from the University of Utah.
Good morning, everybody, and welcome to IDW 2020 on behalf of Anderson and Hauser. This morning, we would like to talk about accurate and reliable temperature profiling in hydroprocessing applications. Before we start with my presentation, let's shortly introduce myself. My name is Stefano Mella, and I'm the Global Product Manager for Temperature Engineered Solutions by Anderson Hauser Group. We, as Anderson Hauser, are a global company leader in the business of process automation. So today we want to talk about effect. So thermocouples in your plant might drift. Some might drift in a positive way, so with the delta positive values. Some others might drift with negative delta values. And here's what we want you to know. So the first question might be, are your sensors drifting? Yes, they do. And considering that the temperature is the most frequently measured process parameter, we believe that this problem is too often being overlooked. Of course, vendors will happily continue to supply replacement equipment, but we prefer to suggest an honest and realistic approach. Why do the thermocouples drift? The reasons can be many, but the basic equation is mostly the same. Critical conditions, together with lower spec instruments, lead to premature failures. And when we have H2S contamination and mechanical stresses on top, then the probability that they drift is even higher. Why should you care then? For sure, to avoid to waste margin, to avoid premature shutdowns and replacement, to minimize the safety risks and assets degradation, and also to avoid to have higher emissions, as well as poor data quality and longer turnarounds. And what must be also avoided is to have high capex for replacement of the sensors. So avoided shutdowns and prevented leak immediately reflecting an instant return of investment. And what can be done? For sure, it's crucial to know the meteorological science behind your temperature sensors. And also, by taking a close look at the critical process instruments will help you to find out the best actions. So, analyzing potential to unlock unit performance is crucial, and we as Anderson Dowser consider you to use the new generation instruments able to have high reliability and diagnostic features. So let's start with the science behind thermometers and more specifically temperature sensors in a way of thermocouples. So here we have a typical thermocouple. You might see it's quite a simple device. It's composed of an outer sheath, a metal sheath, and inside we have an electrical circuit with a hot junction, and the white part is about mineral insulated powder. So when the thermocouple is undamaged, then the hot junction is electrically efficient, it's accurate, and it can enable precise temperature measurement for a reliable process control. This is a typical installation. From the top, we have the complete thermometer provided with its own diagnostic chamber, and going down here, we see the routing of the sensors and some measuring points. What does it happen when a thermocouple sheath gets damaged? Here you might see there is a small white area close to T1 which wants to represent a crack, and the crack can happen because of many phenomena like stress corrosion cracking or hydrogen induced cracking. So when a crack is happened on the thermocouple sheath, then immediately we have a loss of insulation. In other words, the mineral insulated powder gets polluted and also contaminated. And when it happens, new shortcuts and new hot junctions might happen on the thermocouple. Here I want to explain more in details and with an easy animation what is happening on a typical thermocouple. So let's assume we have a damage on the outer sheath, so a crack, and the process fluid goes into the thermocouple. In this specific example, we have a type N thermocouple with an alloy 600 mantle. So the fluid inside the mineral insulated powder will start quite quickly to diffuse into the powder, and from the inner wires outside to the rest of the mineral insulated powder. And the negative effect is a short circuit between the two wires. Here, together with the laboratory, we have tested what are the consequences from the chemical point of view. In yellow, you see the sulfur content, and you see that the sulfur diffused in areas where it is not supposed to be, for example, in the mineral insulated powder. And if we look at the nickel, typical chemical element of the metals, here the nickel diffused from the metal parts to the mineral insulated powder. In other words, those of you which are chemical experts know that nickel and sulfur might cause a nickel sulfide element, so Ne3S2, and this is very conductive. It's very conductive in a way that it can even be more efficient from the electrical point of view than the original hot junction, creating an additional one. How to detect that a thermocouple is drifting? So, when we have a thermocouple sheath which is damaged, then there are effects of T2 on T1. And to answer to this question, we have performed for more than 4 months a laboratory test within the university with very interesting results. Here you might see how the test has been conducted. So we have T1 representing the original hot junction, and we have created in the laboratory an additional short circuit named T2 over the length of the thermocouple. So what has been done is that we have kept the original hot junction T1 at 150 degrees Celsius, and we have changed the temperature of the new short circuit over time from 50 to 150 degrees Celsius. And the test has been ran for about 3,000 hours, which means close to 4 months. And we have not changed just the temperature, but also the gas composition and the fluid composition of the atmosphere around T2. Okay, what are the effects? The effects are quite clear. So all the thermocouples which we have tested had a drift with a downward trend. So all of them were measuring less than what was supposed to be, so less than 150 degrees Celsius. And this downward trend is bigger the more are critical the process conditions. For example, higher temperatures or higher pressures or more corrosive fluids will cause even a higher drift. Something also very interesting was or is described from this graph. So the higher is T2, the bigger is the loss of signal. And the higher is T2 means that the closer is T2 to T1, then the bigger is the phenomenon we will notice. And when T2 overpowers completely T1, then in the control room we will receive a completely wrong signal. As I said, we don't want just to explain the science behind and the problem, but also the solution. So the first question you might have is about, okay, how can I recognize that something like you have described is happening in the plant? Okay, here our suggestion is to use our diagnostic features. Here you see a thermometer with a diagnostic chamber, the blue volume here. And you have to look at the pressure trend over time. We will have hydrogen permeating through the metal flange, and it's a matter of time the hydrogen will also occupy the volume inside the diagnostic chamber. And when the diagnostic chamber is full of hydrogen, then it will reach its equilibrium, which is called the hydrogen partial pressure. Something important, this behavior is due to a physical law and shows that everything is okay. In other words, there's nothing to worry about. Differently, when we have a crack on the thermocouple, then it's again a matter of time and the pressure will increase in the diagnostic chamber. How much? For sure, much more than before. And the pressure this time will reach the operating pressure of the plant. So that's why the diagnostic chamber is a predictive maintenance tool and it's not just an accessory. And this trend shows clearly that the instrument needs maintenance. The question before was, okay, and how can I recognize a drift and how can I take it into consideration? First suggestion is if you have overpressure inside the diagnostic chamber, then your measuring points are no longer to be trusted because, as I explained, it's only a matter of time until the reading is lost entirely or it shows a wrong value. The solution so in addition to the diagnostic chamber, is a new sensor technology we have introduced recently named iTherm ProfilSense TS901. Okay, I like to call it just ProfilSense. It's a new generation of sensors. It's also a patented technology because it has double layers. So we have an outer layer or outer mantle of the temperature sensors, and inside we have additional layers, one per each dedicated thermocouple. And we also have double insulation material. So here we have an outer mineral insulated layer, and each sensor has its own mineral insulated material. In other words, we have double mantle and higher thickness, which leads to a high robust design, able to avoid cracks, H2S permeation, and premature sensor failures. I want to run again the animation we ran before with the new sensor. So in this case, again, we might have a crack, so the fluid can permeate through the profile sensor and diffuse on the mineral insulated powder, and from the inner sensors outside. So the contaminated area will be quite wide, but because of the inner dedicated sheath, the sensors are not affected at all from this contamination. The technology has been tested since many years now, and I want to show you 4 case studies. The first one is about a refinery in Germany, north of Germany, located in Heide, where we have a nitro cracker unit. And the characteristics of this unit is that the temperature is quite high, it's 390 degrees Celsius, and the operating pressure is very high, it's 200 bar G. We do also have 2 other case studies in Germany. Unfortunately, here we have an NDA, so I cannot explain many details about the application itself. But to summarize these case studies, again, we have very critical applications, especially in terms of T1, so the operating temperature, which is about 450 degrees Celsius. If we go to the last case study, this is in Italy, so it's an Ibram refinery. Here we have a nitro desulfurization unit with an operating temperature of 430 degrees Celsius and 75 bar G of operating pressure. So all these customers are happy about the ProFersense technology, and most of them have already switched from the standard thermocouple technology to the ProFersense. Some additional suggestions we can provide are about the reactor internals. So thermocouples need to be fixed inside the reactor, but what you see in this picture is definitely something which must be avoided. And this must be avoided for many reasons. One is because we want to avoid channeling phenomena on the reactors. The second one is because we want to avoid to have pressure drops and hotspots in your reactor, and even to avoid a premature catalyst deactivation. So we, as Anderson Dowser, are used to do engineering studies in order to optimize the installation and also the routing and design of our thermometers. We are able to support to supply self-supporting probe designs. In other words, the probes are much more robust and bigger, and they do not need invasive frames to be supported. What we have tested in all our experiences is that by selecting properly the sensors and by carrying the right installation, we can ensure plus 2-3% increase of productivity of the plant. Here I wanted to show some pictures about the internals. As you might notice, they are very less invasive, so the sensors and the bars are very small. Especially in this picture, you might notice how less invasive we are when it comes to install the sensors. Some benefits which are coming from the ProFersense is because it has this multi-point characteristic. We can use just one frame and install one ProFersense, so routing one cable, and we are able to reach many measuring points inside the reactor. We can also design and supply tailored frames in order to optimize and increase the space for the catalyst so that our complete scope of supply is very less invasive. And now let's go to the last part of my presentation. I want to start talking about untapped margin potential. So reliable, accurate catalyst bed temperature profiling will increase product quality, throughput, and extend catalyst cycle length. Reactor internals, probe design, and smart sensors routing reduces hotspot, channeling, and pressure drops, frees up space for higher catalyst load density. When we talk about environmental footprint, we know that precise control means lower energy input, lower carbon emission, higher conversion efficiency, and lower stress on your assets. So the diagnostic chamber provides additional data and containment layer to reduce the risk of hazardous leakage and preventable incidents. About protecting your assets and critical processes, contaminated sensors for example, because of H2S permeation, are root cause of misleading temperature profiling data. New generation of probe designs with dual shield thermocouples mitigate the risks, prevent shutdowns for premature replacement. And we all know how important is the digitalization, so to have digital plants and to have high data quality. So your process control, operations dashboards, and analytics systems are only as good as the data quality they are being fed. Revamp or greenfield, investing in high performance instruments is always a smart choice. This was my last slide. I want to thank you for your attention and for participating to Anderson Dazer time slot. And in the next 10 to 15 minutes, I will be available for questions and answers. And I also want to invite you in the next days to visit us on our virtual booth, where we can start discussions, know each other, and learn together. So once more, thank you very much. Thanks for listening, and I wish you a nice day and a nice IDW 2020 experience. Have a good day. Bye-bye.
Visit us at www.endress.com.
Thank you for the introduction, and thank you for the opportunity to present this at the conference. My presentation today is titled Improvements in Reliability, Operability, and Performance Revitalize a Vintage SRU. This presentation is a case study of a recent wood sulfur technology project. And I'll present the following topics. First, the background and motivation for the project, review the original scope of the project, and then go over some of the revisions and improvements that were made during the course of the project. Just a quick summary of the current status, and then a summary and takeaways of the project overall. The main purpose of this project was to improve the reliability and performance of an old sulfur recovery unit in a refinery. The refinery had two operating units, one that was designed in the mid-1970s and had no upgrades or modernization during its life. A newer unit was installed in 2005 by Wood Sulfur Group. Both units have a similar configuration of the Klaus unit and incinerator, followed by a caustic scrubber to remove SO2. SRU2, the newer unit, was the primary, and SRU1, the old unit, operated primarily in a standby mode when SRU was down. Recently, the refinery had a change in their operating strategy, and the role that SRU1 played in the overall refinery was upgraded to a more important role. And it was obvious to the owners that the unit was not capable of meeting those new demands. Of course, everybody knows that SRUs don't really make any money, but due to regulatory requirements, they have to have very high availability and have to be operating, or there are penalties, either financial or in curtailing the production of the refinery. Just a quick look at the flow sheet. I want to point out a couple things. That this was the SRU1 configuration as it was operating originally. Basically a 3-reactor Klaus unit with a thermal stage, 3 catalytic stages, followed by an incinerator where all the sulfur compounds are converted to SO2, then a gas-to-gas heat exchanger to cool the incinerator effluent slightly before it went into a water-cooled quench column, and a scrubber with some contacting trays. Then through a booster blower and into a stack after going through the exchanger. The interesting things here and some of the difficulties were, first, the reactor reheat scheme uses a very difficult configuration called hot vapor bypass, where the 2000 degree gas from the thermal reactor or roughly 1,000 degree F gas are mixed with the inlet to the reactors to bring them up to temperature. Very difficult service and difficult control. Also, this gas exchanger was used to cool the incinerator effluent, and it required a booster blower. And you can see that there's a blower at the back end and at the front end of the process. So it's a difficult pressure balancing, and this incinerator actually has a natural draft burner. So there always needs to be a slight negative pressure here, which normally is okay, but any minor upsets and this pressure could go positive with serious consequences. So the goals of the project were to upgrade SRU to increase its reliability so that it could back up the main SRU, SRU2, and eliminate any need to curtail the refinery throughput if an SRU wasn't available. And those improvements are in the area of availability, controllability, performance, safety, ease of maintenance, and again, the end goal being to assure that backup capacity is always available when needed. And this is a visual aid to help people understand what SRU1 looks like. This was a 1974 plant, and 46 years later, it looks something like this. Originally, the owner had developed a scope for the revamp, and their scope included replacing end-of-life equipment or obsolete equipment, which included the thermal reactor and acid gas burner. The burner control PLC was obsolete and was to be replaced, and the sulfur pit had extensive damage and was to be replaced with sulfur seals, a sulfur collection header, pumps, and a sulfur storage tank and loading pump. The reactor reheat scheme, the hot vapor bypass scheme, was to be replaced. This is actually a picture of it here on the right. This very complicated looking valve takes 2,000 degree F gas and splits it off to the reactors for reheating. This is a difficult service, and this valve had to be replaced every 1 to 2 years due to failure. The low performance also results in increased caustic consumption in the SO2 scrubber and increased blowdown water. And instead of the hot vapor bypass, the client wanted to install electric reheaters. They also wanted to put the third Klaus reactor back in service. It had been out of service for many years due to operating difficulties. Update the critical air demand analyzer and the stack emission analyzer. And then another goal of the project to increase its reliability and stability is replacement of the PLC, the control PLC, and institute 2 out of 3 voting on many of the instrumentation, many of the critical instruments. There was also a turnaround that was coming up soon after the project started, which would entail an inspection of all the equipment, in which there could be some additional scope identified. And the client was also looking for recommendations for additional improvements to the safety, reliability, and performance. So the project was executed in the FEL stage gate approach, which is very common these days. The first stage, the FEL1 stage, entailed a review of the process and recommendations and a plus or minus 50% cost estimate. And this stage of the project also identified during the turnaround some additional equipment that needed replacement. It was found that the stack was severely corroded. This picture shows a portion of the stack. It's basically corroded through, and was not in a condition where it could be repaired. There's also the gas-to-gas heat exchanger also showed some severe distortion of the tubes and needed a tube bundle replacement. And the booster blower internals were also found to be badly corroded due to carryover of liquid from the scrubber. Now, Wood's evaluation of this process resulted in a number of additional recommendations. And first one was to improve the control algorithm for the air to the thermal reactor. And then we really wanted to eliminate this natural draft incinerator and the need for the booster blower and heat exchanger. So we made some adjustments to the process, which allowed the unit to operate without the blower. But it needed, in our revised process, the incinerator effluent was going directly to the quencher, so it would see a higher inlet temperature and would need to be replaced. We also replaced the scrubber internals. We recommended replacing the waste heat boiler in the SRU, but the owner did not agree with that. They were happy with the performance of it, and the inspection showed it was okay. So the improved configuration here, first thing to notice is there are now electric reheaters for each reactor inlet. Reactor 3 is back in service. The air control will be improved and a new analyzer installed. The incinerator now is a forced draft incinerator with a blower and operates with the outlet going directly to the quench and scrubber, and then from the scrubber outlet directly into the upper section of the stack. So the FEL2 stage involved completing all the deliverables of the process design package, PNIDs, equipment designs. There was a process hazard analysis, which was done. The detailed engineering scope was developed. Splitting up work that could be done pre-turnaround and during the turnaround was defined. The electrical and control needs were studied and evaluated, and a 3D model of the system was prepared based on a laser scan that was done. And in this phase, a plus or minus 30% cost estimate was prepared. The FEL3 stage incorporated additional discovery items from the shutdown, as well as the process revisions recommended by Wood, updating and extending the level of detail of the project documents, a second PHA, which was done in more detail than the initial one, additional 3D modeling details, and the big part was preparing equipment specs and getting quotes on equipment and major instrumentation, leading up to a plus or minus 15% TIC estimate as the requirement for the next stage. And the next stage is the EP and construction phase, where the procurement process was done. Wood executed the detailed engineering and finalized all of the 3D model aspects for piping, electrical, structural, foundations. Equipment and instrument vendors were prepared, and purchase orders were issued to selected vendors. And then another important part was preparing the detailed scope of work to be carried out before the turnaround and during the turnaround for the contractors who would be selected. And there was close communication with Sulfur Technology Group during the detailed design to ensure that the technology was applied appropriately in these areas. The equipment details are very critical. The layout, piping arrangement, instruments and controls, and operating guidelines were also prepared. And this picture shows a nice triple redundant PLC, which was part of the upgrade to the control system for reliability and high availability. So the scope that was done by Wood's Sulfur Group included, of course, all the process design, equipment sizing, PFDs, P&ID preparation. Several Wood proprietary equipment items were included. The acid gas burner, which was supplied by Wood, and then two critical pieces of equipment, the thermal reactor and the incinerator, and then specification of a number of additional critical equipment items, including the quencher, which would be seeing a very high temperature coming from the incinerator, the analyzers, and the PLC. Interface with the detailed design team, and then bid packages and bid evaluations for equipment and instrumentation. Timeline: the project started back in October of 2018 with the initial FEL1 scope. The turnaround was early in 2019, and detailed engineering started late summer of 2019 and continued on with equipment orders. Recently, mechanical contract was let for the turnaround work and pre-turnaround work. And the shutdown and turnaround are planned for February of next year, and the startups planned for June of next year. So the current status is detailed engineering is complete. Equipment and materials procurement is in progress. Contractors are selected and planning the turnaround and doing pre-turnaround work. Other materials are being ordered, and turnaround planning for spring of 2021 is in progress, with the startup in 2021 midsummer. So again, in summary, this strategy change in the refinery put additional importance on this 46-year-old SRU, and Wood was awarded the contract to do the revamp and identified a number of areas that the client did not originally include in the scope. And you may be wondering why a new unit wasn't built. In addition to the difficulty of identifying space, we believe this revamp also resulted in a 20 to 25% cost savings compared to a new unit. Finally, the last takeaways: the owner knew the unit and was familiar with its performance and knew a number of areas they wanted to improve, but some additional areas for improvement were proposed by Wood, which will improve the reliability, availability, performance, and safety of the unit, enabling the unit to meet all the owner requirements and enable the refinery to hopefully continue profitably with a SRU, reliable SRU backing up their primary SRU. And the result, a nice, modern, reliable unit. Thank you, and we'll stand by for questions.